In our discussion so far, we have looked at different kinds of games and their representations, equilibrium notions, etc. So this is the right time to look at where we are standing currently in the whole spectrum of game theory. So games can be broadly divided into two classes. One is this cooperative class, which will be beyond the scope of this course. We will not be discussing it here. So far what we have discussed are all non-cooperative games. The players do not cooperate with each other. They don't take collective decisions. Rather, they are kind of taking their decisions independently. So in this non-cooperative setting, we have looked at these complete information games. So this branch is what we have already seen so far. So this can be further classified into normal form representation. So games with complete information in the non-cooperative setting can be represented in normal form, and we have seen this is appropriate for games that has simultaneous move, and the equilibrium notions that we discussed, strongly dominant strategy, equilibrium, pure strategy, Nash equilibrium, mixed strategy, and correlated strategies, etc. We have also looked at the extensive form game. It's another representation of the same game, but this is much more appropriate for games which has multiple stages. And we had perfect information and imperfect information extensive form games, and we also discussed about some equilibrium notion in those games. So what we are going to discuss in this module and in the following are games with incomplete information. So this is the kind of games where players do not deterministically know which game they are playing. So let us look at such examples. And of course, there are other classes of games like these repeated games and stochastic games, which we will not be discussing. In fact, given the information that we have discussed so far, we can actually think about different variations or maybe mixes of different kinds of games. Now, what we just said is that in the complete information setting, the things that we have discussed so far, players deterministically know the game that they are playing. There can be some kind of chance moves. Maybe nature plays some probabilistic moves, but those probabilities of those chance moves are also a common knowledge. So therefore, this information, the information about what is happening in the game, is completely available to all the players. In the incomplete information setting, however, the players do not have such deterministic information. So they do not deterministically know which game they are playing. One way of representing that, which we will be doing here, is that players receive some private signals, which we will also call types. And the special subclass of these games with incomplete information that we are going to discuss in this module and the following are these games with incomplete information with a common prior. And this treatment of incomplete information games are due to Harsanyi, 1967. These are also called the Bayesian games, and we will see that where this Bayesian notion comes in to the description of the game. Let's begin with one example. So let's say in a soccer game, there are two competing teams who are clashing against each other. Now, each of these teams can choose a game plan. So game plan is like the ideation or the plan how they are going to play. So they can either aim to win or maybe aim to draw. Their moves on the field will largely be governed with what game plan they start with. Now, this game plan we will call in the terminology of incomplete information as their types. These are private signals only to them. So for instance, you can think of that these are like caused by certain external factors which are only known to them. Let's say the weather condition. Some of these teams might be able to play in very hot conditions, very cold conditions, etc. Player injuries. This is something that only the respective teams will know, their fitness levels. And then also depends on the ground condition. If it is very wet, maybe some teams have certain advantages. So based on that, they can choose which kind of game plan they want to play. Now let's say once we have chosen, so these types are either win type or draw type. Based on that, you can think of there are different type profiles in this example. So either both of these players are playing to win, aiming to win. One player is trying to win, the other player is trying to draw in these two cases, and both players are trying to draw, right? The payoff matrices, so the whole idea of incomplete information game is that when you have chosen a specific type, you are actually in a different game. So if the players have chosen their types, the type profile determines which game they are in. So for instance, if both these players are trying to aiming for winning, then if both of them are attacked, so then they have two actions or two strategies available. They can play attacking or play defense, right? So in this world where both are trying to win, maybe both teams are quite well equipped because they are kind of playing very aggressive. So if both of them are playing attack, they get equal payoff, which is like 1. Now when one player is attacking, the other player is defending, because this player 2, was actually trained for winning, that is, they were trained to play aggressive, so they might not be good at defending if they play defense. So in that case, they get 0 payoff, the other player gets something positive. I mean, the numbers do not really matter, it's just exhibiting that depending on which kind of player, which kind of types are chosen by these players, the payoffs may be different. So if both of them play defense, none of them do well, so maybe they get low payoff. Similarly, if the first player is trying to win and the second player is trying to defend or make a draw, then the payoff will be a little different. And this will be different when both players are playing defense. Both players are playing for securing a draw. Now the game essentially is changing. So the fundamental difference of this kind of a game with that of complete information is the players. So maybe player 1 knows that which type it has chosen, but it cannot observe what is the type that has been chosen by the other player. So they do not deterministically know that what is the which one of these games they are playing. So if they're picking player 1, let's say is picking W, then it knows that either it is playing this game or this game, because the W is remaining same, but it does not know what is the other player's type is. These are private information. So therefore they have an uncertainty about the game that has been played. So in this setting, the assumptions that we are going to make is that these probabilities of choosing these different games, with which probability you will be choosing the types and therefore the games, they come from a common prior distribution. So this is a crucial assumption. There is a common prior which is governing how people are picking their types. And the second assumption is this common prior, not the realization of those of the types, rather the distribution of those types are common knowledge. So these are the two basic assumptions. Now we are in a right stage to define what is a Bayesian game. So Bayesian game, like the normal form game, is actually defined with respect to the following information. So the first information is the player set, of course. The second one is the set of all types. So this theta I, capital theta I, is actually the set of all types of player I. The next element in this tuple is the common prior. So this is the probability distribution over the type profile. Right? So an element of this capital theta will be something like theta 1 for player 1, theta 2 for player 2, and so on. So in the previous example, you can think of that this theta 1 can take two values, either W or D. So similarly, you can think of if there are multiple other types, and this type sets need not be same for every individual. So this is the type profile for these players, and this function P is actually giving a probability distribution over all such type profiles. Of course, this probability has one restriction, that the marginals, if you take the marginals with respect to any theta I, then it has to be positive. We'll see where it is needed. This is actually required to define the conditional probabilities. But even otherwise, if you think of a particular theta I where this marginal is actually equal to 0, then we can actually prune that that theta I from the set capital theta I, because the probability of that occurrence of that theta I is 0. So therefore, why should we actually keep it in the set? So for all the elements that are living inside this type set theta I, the marginal probability for that theta I is positive. Now the last element in this tuple is this gamma of theta, and gamma of theta is the normal form game. So it is the normal form game when the type profile is theta. So think of one of those previous examples. Once you have fixed the theta, let's say theta is equal to this, so theta 1 is D and theta 2 is also D. In that case, you know that which game you are playing, and this is essentially going to be the gamma of theta in that case. So yeah, the representation is pretty simple. You have the same set of players, you have the action set. So in general, the action set can also depend on theta. So whatever this type profile is, based on that the action set may differ, but we'll be assuming that the action sets are always going to be the same. It does not depend on theta. So the last one here is the utility functions. So we have seen that in the previous example, the utility. So this is the UI. So U1 of theta, and this is given by the action profile that both are attacking. Right? So this is the utility, and that is represented by this element in this tuple. So utilities in this case, so in the context of Bayesian games, the utilities are not only functions of the action profile that has been chosen by all the players, it is also dependent on the type profile, where A is the Cartesian product of all these individual sets of actions. Now, what are the different stages of this Bayesian game? First, with the common prior assumption, these theta i's are generated with respect to this common prior P, and then every player just observes its own component. It cannot observe other players' components. They are private information of those players, and then based on that information they will have to pick an action which lives in this action set AI. And once every player has picked their action, every player is realizing some sort of an utility. So that is given by the actions that has been chosen by these players, and also based on the types that has been realized with respect to this common prior.